Well, thank you so much. And thank you guys for inviting me over. I appreciate it a lot. So today I'm going to present the Epsolute. It's a part of my doctorate work. In general, what I did on PhD was trying to build different query types engines, like point queries, range queries, KNN queries, so that at some point we can compose an entire secure outsourced database system from it. And this particular component concerns point and range queries, mostly range. They are more interesting, in a persistent adversary setting. So let me get started then. I have a couple of sections. In this one, I will cover some background pieces, like what the outsourced database is in the context of this work, the concept of differential privacy, and ORM. Let's get started with some motivation. There are vast amounts of information that companies are processing and storing, and they increasingly turn to cloud solutions. That is outsourced databases. But these solutions need to be both efficient and secure to be practical. As we have seen in the past, there are recent attacks on access pattern leakage and communication volume leakage. We differentiate two types of adversaries generally in outsourced database setting: the snapshot adversary and the persistent one. The snapshot, as the name suggests, he can grab a snapshot of memory at any point in time. It's a weaker adversary, and then given the memory snapshot, adversary tries to infer some information from the possibly encrypted data points. The persistent adversary can do everything that the snapshot can do, and on top, he can monitor the what's going on the server, specifically the access pattern, the pattern of accesses that the client, the program on the server makes to its external storage, and communication volume. That is essentially the network traffic, the timing of it, the size of it, the frequency of it, everything. And there are attacks which show that the access pattern leakage or communication volume leakage alone is enough to do even a reconstruction attack in some circumstances. So when we build a secure outsourced database, we need to take care of this leakage. There are some existing solutions in the outsourced range query engines. Some of them only concern snapshot adversary. These are some of the earlier works like CryptDB, Arc, CBET. Obviously, they do not account for access pattern communication volume, so they are weak against the persistent adversary. There is also a line of works where people use trusted execution environment, also known as enclave, like SGX. But again, there are some cons to it. This hardware is uncommon. It usually has very limited memory, like 100 megabytes at most. And most of all, even Intel, the creator of SGX, the most widely used enclave technology, they have recently deprecated SGX entirely. They essentially confirmed and acknowledged that it's insecure. And there are other solutions which are more similar to what I will present. They try to protect against access pattern communication volume, but it's either they protect against one of them but not the other, or they use very expensive protocols or primitives like a linear scan or full padding, which makes it secure but doesn't make it efficient. And as a consequence, I present Epsolute, which we deem most secure and practical range and point query engine. In the outsourced database model I described, it protects both access part and communication volume in particular using differential privacy guarantees, and it does not rely on enclaves like SGX, linear scan, or full padding. Some concepts to get us started. We model database as a set of tuples where each tuple consists of a record which has a unique ID, a search key, you can think of it as an attribute, and the payload, which we simply encrypt. A query in the outsourced database is essentially just a predicate which is evaluated on a search key, on an attribute. And evaluating a query on a database results in essentially determining which records satisfy the query. So the evaluation of a query in its simplest form does not do any manipulations. It simply tells which records are in the result set and which are not. And in the outsourced database system, we try to devise the protocols which are query type independent, sort of, now that a query is just a predicate. And we say that, first of all, outsourced database system consists of a user, a trusted component, which is usually a thin client, and a server, which is large, powerful, but generally untrusted. And the persistent adversary can monitor the server only. And we have two protocols, setup and query. Formally speaking, in setup, user receives a plaintext database and does something with it and outsources it to the untrusted server. The server can generate some auxiliary data, like we will call it the data structure DS. And in the query protocol, the user receives a query. The server maintains the state and this auxiliary data structure, and they do some communication, at which point the user outputs the result of evaluating a query on a database. Essentially, user returns to the application the records in plain text which satisfy the query. Formally speaking, for correctness, we require that for any database, for any sequence of queries, it holds that running the protocols yields correct results. So essentially, we do allow some degree of approximation, but with overwhelming probability, the query result has to be basically correct. The next building block, differential privacy. I'm sure you all know it or heard of it. Let us formalize. First of all, differential privacy is a property of an algorithm. It's not a construction or an algorithm by itself. It's merely a property. And that property says that suppose you have two databases, which again we model as the set of records, and these databases differ in exactly one record. We call such databases neighboring. And then we say that differential privacy says that the view, well, let me paraphrase it. For two such databases, the probability that by looking at the output of the algorithm over the database, one can reliably tell which of those databases was used, such probability is bounded by differential privacy guarantees, namely by this formula and parameters epsilon and delta. Essentially, differential privacy, as the name suggests, protects a privacy of an individual. You cannot tell whether the individual record was or was not in a database with this and this probability. And the way to make sense of these probabilities is epsilon e to the epsilon can be approximated as 1 plus epsilon for small epsilons. So epsilon is essentially an absolute difference in probabilities. If epsilon is 0, probabilities have to be equal. If epsilon is large, the probabilities can differ in absolute terms. Delta, on the other hand, is an additive term by itself, so it has to be small. And one can think of this term is if a differentially private mechanism is used in a system which can fail with certain probability, like an approximation algorithm, then delta will encompass this probability of failure. As we will see in the rest of the talk, we are using differential privacy in conjunction with the RAM, and the RAM can fail, for example, pathoram. So this delta would essentially be a probability of a general system failure, because if such event occurs, you cannot guarantee privacy. Now that I said that differential privacy is only a guarantee on an algorithm, the question is, how do you make an algorithm differentially private? Luckily, there is at least one way suggested by the authors of the original differential privacy paper, calibrating noise to sensitivity. So they essentially say that if you know a sensitivity of your query, that is how much your output changes if you change an input. And you have your epsilon privacy budget. Then if you add noise from a Laplace distribution with a scale sensitivity over epsilon, then the resulting mechanism will satisfy epsilon differential privacy. Now you can ask, okay, but Laplace distribution is symmetric. And if we add noise, we obviously shouldn't add negative noise, especially if you use this noise as a count of your records. Otherwise, you will return incomplete result, which would violate our correctness guarantee. What you can do instead, and I will show you in the rest of the talk, you can shift this distribution, because the guarantee says that it has to be a proper Laplacian distribution. It should not be truncated. It doesn't say that you cannot shift it. So you would add some value to all of the samples. You essentially shift the mean. You can shift it as much as you want, but you are essentially bounded. If you shift it too little, some of the samples will be negative and it will break your guarantees. But if you shift it too much, you will add so much noise that your system will be inefficient. So essentially you are striving to find an optimal shift. And I will show you how we do it in Epsolute. And finally, differentially private sanitizers. The way I just described with the Laplace perturbation algorithm, you can only add such noise for one query. Because if you keep sampling new values from Laplacian distribution for each query, a clever adversary will be able to filter out your noise. So if you want to support an arbitrary length of query sequence, you need to use what we call differentially private sanitizer. A sanitizer is a pair of algorithms which produce a sanitizer object, let's call it that, with certain guarantees. Formally speaking, sanitizer is a pair of algorithms where one of them is differentially private, and it outputs a data structure, let's call it DS, such that a second algorithm, algorithm B, can use that data structure and a query and give you the result with certain guarantee. And the guarantee is that with probability 1 minus beta, you can control that beta, the result of the query will be within alpha of a real query result. And remember that evaluating a query on a database only marks records as in result set or out. So when we say alpha of real query result, that means that if, for example, your real result is 100 records and your alpha is 50, then whatever this algorithm B produces has to be within 50 of your real 100. Now about sanitizers, there are some known constructions and there are some known bounds. When analyzing our absolute constructions theoretically, we're interested in, at least asymptotically, how much noise would using such a sanitizer add. And we have from different works in the literature some bounds for pure differential privacy and approximate, that is your delta 0 or not. In pure, it's 0. And for point and range queries. Now, a little background. Point query is the one where you essentially say where an attribute equals a single value. We call it categorical query. For example, you have a set of students in the class and you say, give me all female students. That would be a point query, a categorical query. Even if the result is more than one record, it's still a point query. A range query, it's a simple one. You essentially say that the attribute has to be within 2 endpoints, like give me people of ages 18 to 65. And for these queries, there are different bounds. I also wanted to visualize at least one instance of a differentially private sanitizer so that we know what we're talking about, what this structure DS can look like. For example, this is on the right, is a hierarchical range query sanitizer. Suppose that we have our data set and suppose that the domain of this data set is 80. For example, it can be patient's files, and the index attribute, the search key, is age. So we have people ages from 0 to 80. What we do is we first split this domain, and that's important, domain, not the actual data set, but only the domain. We split it in buckets. There is some logic on the choice of bucket, but for now, let's see that it's a 10. Then in each bucket, you sample from Laplacian distribution shifted, so that all of your samples, these red pieces, like 5 here and 6 here, the red pieces are samples. You have to shift it in a way that the samples are still from Laplacian distribution, but they are never below 0. Suppose that we have sampled it, and then in each of these buckets, I also put on the lower level the number of actual data points which you have in your data set, and you sum it up. So essentially, in each of the bucket below, you have a noisy count. In here, you used to have 13 records, but now with the noise, you will have 18. And you do the same for each of those buckets. That would essentially produce you a point query sanitizer. What makes it range is that when you do a range query, you can potentially span more than one such bucket. And of course, you can simply return the number of records, which is shown by the sanitizer, and you will still be correct and secure from the differentially private standpoint. But you can do a bit more optimally. We can say that these lower buckets, we group them by parent, and we add noisy count to the parent node alone. So you see that we add 13 and 12, the real counts are added, because in the range 0 to 20, you have 25 real records, so it will always be there. But now, instead of the summing up noise, 5 plus 6, we are sampling a new noisy value, which makes the combined number of records smaller. And how we answer a query, we do what's called a best range cover. For example, if my range query is, say, from 5 to 25, I use these 3 buckets because I have to pad it to the fullest. I cannot take half of the bucket. But now I see that although the 3rd bucket has to be like this, the 2 other buckets, they can be composed into their parent. So now, instead of doing like we would do in a point query and return these 3 buckets, I would return these 2, which would technically result in less noise. In this picture, I show binary tree, but in reality is going to be k-array tree, which is usually 16. There is even a theorem that proves that 16 is optimal. So essentially, by tuning the number of buckets and the fan out of such a tree, you can essentially optimize that your ranges, which you expect, will try to grab the parents. But one of the things to remember, first of all, we do bucketing on domain, not data, and we outsource as a sanitized data set the counts, the sums in these buckets. And it has been proven that this structure alone does not reveal anything about the data set, at least from the differential privacy standpoint. We don't have to keep the structure private. The server can hold it. All right. Now that we are done with sanitizers, the last piece is the composition theorem. What happens if you have R mechanism that operate on R different data sets? How do you compute the combined, the composed privacy budget? The theorem says that depending whether your data sets are joint or non-disjoint or disjoint, you either get the sum of the privacy budget as your privacy budget of a system, or the maximum privacy budget as your system privacy budget. We'll use it later, I will show you. And now the the other piece we will use in Epsolute construction, ORM, which protects access pattern. I'm sure you have heard of it. The access pattern is essentially defined as the sequence of memory accesses, where each access has a location, essentially an address where the access is made, the type, whether we are reading a value or writing a value, and a data point to be written if we're doing a write. ORM is a protocol between the client and the server, and it guarantees that if adversary is monitoring the server, the adversary will not be able to distinguish one access pattern from the other, provided they are equal in length. So if you are accessing 5 data points in the left and the right worldview, even if you access the same location multiple times, adversary will not be able to tell. And although the ORM concept itself is very old, it's been published in May 1996, almost in my birthday. There are many constructions now that do ORMs, with PathORM being the most used of those. And we are using that in our construction. One thing to note about ORM, although there is a protocol and it probably conceals access pattern, it does that at a cost, which is by theoretical bounds no less than logarithmic in the number of stored records. So if you have 1 million records, then expect that about 17 extra accesses you will make for every real access you need. All right, now about the Epsolute. First of all, the definition. We are starting from the theory, from what we want to build, and then go to the construction. And our question is, can we come up with a definition of a system in outsourced database model such that being secure in this definition would probably protect access pattern and communication volume with some meaningful guarantee? Our answer to that is computationally differentially private outsourced database system. Here, the way to interpret it is the view of the adversary on the untrusted server while we execute M queries is essentially an algorithm which we protect with differential privacy. So what happens here is we have 2 neighboring databases. We have M fixed queries. We execute these M queries in our model. We let adversary observe the entire execution of all M queries on the server. And we guarantee that the adversary will not be able to tell which of these 2 databases was used with this guarantee, which is essentially a differential privacy guarantee. The pros, the advantages of our definition are manifold. First of all, we protect the entire view of adversary with differential privacy. There are works which try, for example, to protect only the access pattern or only the communication volume. They treat it as a statistic which you need to protect. Instead, we protect the entire view. Whatever adversary sees is protected. Obviously, it implies protection against communication volume and access pattern, because if I see as an adversary any of those, I can break the definition. I can tell which of these 2 databases was used. The query sequence is fixed, and on the next slide, I will tell you why it's inherent. And finally, the negligible term, which we have added, you haven't seen it in the other differential privacy definition. It's to account for computational as opposed to information theoretic DP definition. In computational security, the security itself depends on the fact that the adversary has limited, or say non-infinite bounded computational resources. In information theoretical, there is no such assumption. We need computational security because some parts of our system will essentially use a plain old encryption, and it in itself provides only computational security guarantee. Now, why is the sequence of queries fixed? it's essentially a question that was asked in the CCS presentation. We claim that adaptive queries are impossible in our definition. And here is why. I will show it to you by example. Remember that adversary wins if adversary can distinguish two databases. Suppose that in our example, we have two medical databases that differ in one record as per differential privacy setup. And that one record is with the rare diagnosis Alzheimer's disease. Now remember, in differential privacy, adversary is allowed to know all the data points. I'm not sure if I told you that. The data points are not secret. Adversary knows database 1 and database 2. Adversary only doesn't know which of those databases is used. So adversary knows that the two medical databases differ in one medical history with Alzheimer's disease. And we know that such a disease correlates with age in population. Now suppose that adversary knows, it's a public knowledge, that a user, a medical professional, not an adversary, queries the database in the following fashion. First, the professional queries the condition Alzheimer's disease specifically. It's a point query. Obviously, our system needs to protect it, so we will return noisy count anyway. So adversary can expect to see, I don't know, 2 to 3 records, but adversary will not be able to tell if the real record was there or not. But the user sees the answer. And if such record exists, if such a query for the user returned a medical history with Alzheimer's, the professional will query the senior patient next, because professional knows that such a condition correlates with senior population. So the query will be, give me all seniors. It's going to be a range query. Otherwise, if there is no Alzheimer's disease, the professional, for their own reasons, will query the general population, and it will result in many more records compared to the seniors. Now, the beauty of this example is adversary can observe the size of the result of the second query. Adversary can deduce whether professional queried seniors or all patients, and the adversary can conclude the result for the first query. And therefore, adversary can tell whether Alzheimer's was or was not in the database and can break our definition. Obviously, we can try to return the same, roughly the same amount of records in seniors and in all patients, but it will be inefficient. So our claim is it is impossible to execute queries adaptively in our definition and yet stay efficient. All right, now the construction. We have built Epsolute. Here is the single-threaded construction, which probably satisfies our definition. It consists as an outsourced database of 2 parts, the untrusted server and the trusted user. The trusted user stores a record index, a mapping from the search key from the attribute to the record ID. And that's all. The adversary, the untrusted server, holds the ORAM storage and the sanitizer. In the setup stage, the user generates the record index and interactively with the server generates the DS structure, the sanitizer. Essentially, the user generates it and outsources it to the server. And on the query stage, the user does the following. Suppose that the query asks for salaries 40K to 50K. The user goes to its own local index and retrieves the IDs of the records which would truly satisfy the queries. Then the user goes to consult the sanitizer structure and gets the noisy counts. For example, the record index tells that we need to return 6 records in total. The sanitizer will tell that you need to add another 5. So your total will be, say, 11. And then the user uses ORAM protocol and retrieves all the 11 records using ORAM, which would result obviously in many more records. But in the end, the adversary on the server only sees the noisy counts. So the adversary only sees the 11 accesses. Adversary doesn't know that the original was 6. And because of ORM, adversary doesn't even know which particular records were accessed. That is Epsolute for you. Now, how exactly do we construct the sanitizers? We use a usual regular histogram sanitizer for point, and I will tell you the hierarchical one for range. Now, remember I told you that we need to shift a distribution for Laplacian in a way that it's shifted as little as possible, but does not result in negative samples. So what we do essentially is we know the number of buckets which we will need samples for, it's n. And we know the probability of a failure, it's beta. So we do some algebra and tell that the optimal value of alpha, the new mean, has to be this, so that with probability beta, which is already our probability of failure, we will not get a negative sample. So we have this global probability of failure in the system, and we try to tailor all the components to this probability. In particular, a sampling of a negative value would break the system. So we make sure that such an event happens with probability beta. And the alpha to do that is shown in this formula. Now, for the range queries, we use hierarchical sanitizer like the picture showed you before. We know that the optimal fan out of such a tree is 16. So essentially, it's just a slightly more complex formula, but we know the number of buckets in such a tree. So we use the same method. We compute alpha in such a way that with probability beta, it will fail. Let's say with probability 1 minus beta, it will succeed and will sample only non-negative values. Now, how do we analyze our solution? We use two metrics, storage efficiency, communication efficiency. And let me explain those. Storage efficiency is defined as the sum of the bit lengths of the records relative to the bit length of the corresponding encrypted database. So when you do encryption, you are allowed to add some more data to it. I don't know, initialization vector, some auxiliary data. So the storage efficiency is how much more do you store on the server compared with what would we call optimal, the bit lengths of your real records. The communication efficiency is defined similarly. You have a number of records which you would return in a plain text database, and you have a number of bits which you actually return in Epsolute. So the efficiency is the optimal relative to the actual. And mathematically speaking, we define efficiency with two values, the multiplicative term and the additive term. So if you have your ideal value as n, your actual value is a1 n plus a2. You have a multiplicative term and the additive one. And we have analyzed our Epsolute in this regard, and we concluded that the storage efficiency is constant 0. So we have a constant enlargement in the bit length of the database and 0 additive term. And communication efficiency, it depends on the sanitizer which we use. And there are different values for pure differential, pure and approximate differential privacy and point and range query. And the usage of ORM also adds the communication overhead. And you see these values. Finally, I want to mention that the Epsolute does support multiple index attributes. So you can tell something like, give me seniors with people from 18 to 65 and females. So it's possible. How do we build it? The naive way is to simply duplicate the entire states of user and server and use one such copy of state per attribute. So we duplicate ORM storage, we duplicate differential private sanitizer, record index, everything. But we can do it more cleverly, and we can note that only the ORM state which holds the actual payloads of records, it stays the same for all attributes. The thing which differs is the differentially private sanitizer, because it's one per attribute and one per query type, and the index. And we show in experiments that those little things which are different are very, very small in practice, and the ORM state is the largest, and it stays the same for multiple attributes. One of the security privacy consequences of that is you also have to split your privacy budget among your attributes, and for that you use composition theorem, which I talked about. In our case, it would be, I don't remember joint or disjoint, but you essentially cut the privacy budget for an attribute from the system. So if you have your epsilon, say ln2 for the entire system, if you split it into two attributes, it's going to be ln2 over 2. But now you can reasonably ask me, is it efficient? The Epsolute uses ORM, which is by itself kind of expensive, and we even do extra records resulting from noise. Yes, single-threaded version is very slow, but we can parallelize it. So our second contribution is the parallel construction. What we do here is we split user and server states, that is the data sets, the encrypted data sets, into M ORMs. And we run these ORMs on separate machines in parallel. We partition the records by ID, or say by hash of an ID, into M partitions, and generate a separate index for each of these M components. But the question is, what do we do about differentially private sanitizer, this tree structure for range queries, which I showed you? Should we generate one of them for all partitions, or should we keep a separate one for each of them? We did both, and we compared. There is a no gamma method. Don't ask me why we call it no gamma. It's a legacy. When we maintain a separate sanitizer, separate structure per ORM, now each of those ORM will incur noise comparable to the single-threaded version, because even though the amount of data changed, the domain didn't. And you remember that the amount of noise we generate depends only on domain. So you essentially multiply the amount of noise because you now have M partitions, but you split your real work into M partitions. So your ORMs are now processing together the real work as in single-threaded, but you multiply your noise times your number of partitions. The second option is gamma option, when we do shared sanitizer implementation for all ORMs. First of all, we now do the same number of total records for each of the partitions. We generate the noise in such a way so that we pad for each of the ORMs is the same number, so the adversary cannot distinguish. Such approach results in somewhat larger noise than the original single-threaded, but not by much. But now you split all of these values evenly among all ORMs. So now you process the same number of real records, and you spend on slightly larger noise. And the question is, which of them is better? Obviously, by the simple arithmetic, if your alpha term, the one which is your multiplier on your noise, if that term happens to be less than your parallelization factor, then gamma option wins. And we show practically that for pretty much any M, for even the smallest M's, the gamma option, keeping shared sanitizer for all ORMs, is better. And here is the construction when we put all the components together. The idea is the same, but now we parallelize certain stages. The user makes a query, say we need ages 18 to 21. This query goes to the client. The client fetches the true indices of records from its local index, like b+3. Then the client goes to sanitizers and gets the noisy counts for each of the ORMs separately. And then the client runs these ORM protocols in parallel for each of the MORMs. and then gathers the responses, decrypts them, and gives it back to user. And that results in much faster execution and still secure. And now experiments. Now we want to measure the efficiency of our Epsolute construction. Here is our experimental setup, our default setting. First of all, we implemented everything in C++, PyTheorem implementation from scratch, and even B+3. We use OpenSSL for crypto. We need at least encryption for ORM. We ran everything in the cloud, in GCP, in different regions. That one is important. I've done a lot of related work analysis, and only a few works truly run outsourced databases in different geographical regions, because that is the fair approach. We did it as well. We use 3 data sets, 1 synthetic uniform, and 2 real salaries data sets. I believe 1 from public California employees and 1 from census. And we generated these data sets of sizes 100,000, million, and 10 million. In our default settings, the differential privacy parameters are consistent with the literature. Epsilon privacy budget is ln2, and beta, the probability of entire system failure, is 2 to the minus 20. We have the default setting on a uniform data set, 1 million size, and the record sizes are 4 kilobytes. That's important because our ORM actually retrieves the real records and decrypts them. So when we measure the efficiency of Epsolute, it is important that we don't do it kind of virtually or logically, we do it physically. Larger records obviously result in larger overhead. The selectivity of our range queries at 0.5% in the default setting. Selectivity is the fraction of records which are returned in a query. So 0.5 means that we have like 5,000 records per query. And we use gamma method because it's faster as a default. Besides Epsolute, we want to compare to other database solutions. On one side of the security spectrum is conventional MySQL Postgres database. It is configured for 0 security, but maximum efficiency. And as you can imagine, a typical database is very optimal for range queries, for indices, even for reading data sequentially from a storage. And the other side of the spectrum is, what if we download every query? We encrypt the entire database symmetrically, upload it, and every time we need to execute a query, we download it, decrypt, and execute. We call such approach linear scan. We compare ourselves with them. And there is a shrink wrap. The shrink wrap is not specifically for range queries. They are trying to execute SQL queries in a federated model, but it's got to be a general SQL query. So they support joins, projections, range queries, point queries, everything. We have contacted the authors of the paper. They have shared the source code. We have extracted a range query component specifically, and we have used it as a baseline for comparison. Question number 1, how practical is Epsolute compared to other solutions? I'm glad to say that Epsolute is only 8 to 4 times slower than the conventional non-secure MySQL and Postgres. You can take it with a grain of salt because Postgres does not need large server to be so fast. Epsolute does. But again, we've been able to show that in certain settings, Epsolute, in a default setting for Epsolute, it is only 4 to 8 times slower than the conventional database. The linear scan, the one which downloads everything, is 15 seconds. It's about, 17 times slower than Epsolute. And we did linear scan a favor. We let it download everything with the same parallelization factor as our Epsolute, which is 64 threads in the default setting. So even when you have 64 threads simultaneously downloading the database, even though you use very fast Google's regional data bandwidths, it's still 15 seconds per query. And the shrink wrap is surprisingly 20 minutes per query. Why? Because to be secure, they use linear scan, oblivious sort, and garbled circuits all at once. So it's very secure, very flexible, but just prohibitively slow. And Epsolute is much faster than that. I think I computed 3 orders of magnitude faster. And on the right plot, you can see if we try to range the record sizes, for the linear scan, the record sizes, data sizes, and threads, that's how the linear scan behaves. The 15 seconds is the default. So you can see that for linear scan, the number of access threads don't really make a difference. But there is a big difference if you add the record size. That's why we specifically tell which record size we use. Now, the second question, and we've been asked by the reviewers, what about storage? After all, our client holds the record index, and our client holds ORAM client state, and our client holds even the differential private sanitizer. Although in theory, we can outsource it to the server, practically we keep it on the client. So here we show the values for different record sizes, different record numbers, and different domains, because the record size obviously affects the storage size, because the server actually stores that much data. The number of records affects your record index. The more records, the larger the index is. And the domain affects the differential private sanitizer, because that exclusively depends on domain. Now you can say that for the default setting, the ratio, the ratio of the client storage to the server storage is already large. It's from hundreds to thousands. So even though the client stores 3 different components, they are very small in practice, and the server storage is very large. So we conclude that the Epsolute storage requirements are efficient and practical. The third question is, what happens if we start to vary some parameters? In the paper, I have many more plots, but here, for example, let us vary the selectivity, the number of records the query returns. We've seen in our experiment that this value is essentially the main determinant of the absolute efficiency, because your selectivity implies the number of real records, which in turn implies the number of total records you fetch. And you can see that it scales almost linearly. And depending on epsilon is exponential in the differential privacy definition. So you can see that the amount of noise grows exponentially as epsilon decreases. Now, how scalable is our system? When we introduced parallel Epsolute, our premise was that we want to scale with the parallelization factor. Obviously, ideally, we should scale linearly. And I'm happy to tell that yes, at least for gamma method, when we store 1 DP sanitizer for all ORMs, the scaling is almost linear. And on this plot also, you can see that the gamma method pretty much outperforms no gamma when you maintain separate DP sanitizer for all M's. For 96, it's different because GCP does not support 128 CPUs. So some of the ORMs had to share a CPU. Question 5, multiple attributes. What the impact of supporting multiple attributes? Because we have to split the privacy budget in 2. I am happy to tell that the difference is minimal. We have run only one attribute or only the other. Then we run them in alternating fashion. Or we store both index attributes, but query only one. In all cases, the difference is minimal. So supporting multiple attributes, we conclude is efficient. That's all. Thank you very much. I think I a little bit went over time, but I hope it was interesting to you.